Okay, I guess I can get started. Yeah, that's almost certainly working that. So. The next set of worksheets on chapters 15 through 22 is due on the 30th. As is homework number 3. The semester project topic is due today. I extended it today. Please choose a topic that hasn't been claimed. You can see the list of claimed topics by going to Brightspace. I'll just show you if you go. I'll go away. If you're in Brightspace, you can look at content, semester project, and there's a list of claimed topics here. And I update this as I mark new topics in. So choose something that is not on this list of claimed topics. And here's a list of examples. Let me just I don't want to see what just got submitted. Someone just submitted a topic. Which I will handle after class. So you are not limited to the example topics. You can choose a topic that you make up on your own. Oops. Midterm is coming up. It's the end of the week. By the midterm, you need to meet the active pursuit requirement. It's fairly straightforward. You need to have taken all tests. Well, it's the 17th to be precise. But if you get it done by Saturday, it shouldn't be a problem because my grades, when I have to make the decision, are due on the 19th. So getting it done by Saturday is probably okay. But don't push it. Need to have completed at least 50% of assignments. That's homework, worksheets, etc. And taken all tests. I know there's at least one of you who was sick for the last test, but arrange, set up a plan with me for that. I accept having set up a plan for retaking the test as taking the test. That's acceptable. But if I haven't heard from you about it, you need to get in contact with me and arrange to take the test. But yeah, get half the stuff turned in. Doesn't have to be great, just has to be turned in. So, I mean, you can get away with, I guess you can get away with all the multiple choice assignments and a few of the short answer ones or one of the homeworks. You're not going to have a great grade that way, but that would meet active pursuit. You just need 50% of assignments. So if you're trying to catch up to that line, I would suggest start by doing all the multiple choice ones because those are going to go faster. Yeah. And please sign in on the sign-in sheet if you haven't already. Are there any questions? Oh, and I just noticed something this morning when I was looking at things. Sorry if you were panicking about your grade on test 2. I had the wrong total set into the grades on bright space. I just corrected that, so everyone's test two scores just shot up as a percentage. Because in the past, I did a 75 question test and I hadn't changed the grades. I hadn't changed it in the grade sheet on Brightspace. So I just noticed that just before class. Sorry about that. I was looking at it, it's like, those all look off. And then, oh, they're out of 75. So I fixed it. So you all should have seen your test grades go up. Sorry about that. I just missed it when I was correcting things. I have fixed it for the future tests. Now that it's fixed, it won't affect your midterm grade. I do not do test retakes. I would send me an email about that. I can't talk about that now, like in front.
Never mind. My grade is good.
So
I
some of
don't
the
think
fact that I just fixed that. It should have been out of 60, it was out of 75.
yeah, I said that before you just said that.
Okay. Um, sorry about that mistake. Um, and I fixed it already for the other tests. It was just that this semester I was changing to shorter tests. And so I missed it. Okay. That's all the stuff for midtermy stuff. Yeah. Okay. So let us look at ionization and temperature. So if we look at ionization and temperature, it turns out different things ionize at different temperatures. So if we look at which gases or molecules are ionized, we will see, we can get information about the temperature. So the level of ionization also reveals a star's temperature. So this is another way to figure out the star's temperature, other than just its color or its peak wavelength. And the advantage of this method using ionization is that because it's based on absorption lines, it is not affected by, say, something in the way like dust distorting the color. So dust can scatter away shorter wavelengths and make stars look redder and thus cooler. But if you look at the ionization, you'll actually get a better idea of the temperature. So by looking at the absorption lines in a star's spectrum, we can figure out its ionization level and work out temperature from that. So stars get classified by their spectra, and different substances will have stronger absorption lines at different temperature ranges. And it's not like a simple direct relationship. It's a bunch of stuff peaks at different times. So all stars have more or less the same composition, hydrogen, helium, and a smattering of extra stuff. And the visible lines depend on the same temperatures. So for example, cool stars down here aren't hot enough to excite the hydrogen, but can be cool enough to still have, certain molecules in them. Hot stars will ionize the hydrogen and can also tear molecules apart. And at about 10,000 Kelvin is the best temperature for ionizing hydrogen. And stars And then hotter things, you'll eventually completely ionize the hydrogen, and so at about 10,000 Kelvin is the best for exciting hydrogen. Eventually you ionize the hydrogen and the hydrogen lines vanish. Because ionized hydrogen doesn't have any electrons left, so it doesn't have any absorption lines. And then you can have neutral helium and ionized helium and such. So, and you may have noticed these letters seem kind of random. It goes, from hottest to coolest, it goes A, O, B, A, F, G, K, M. Because the original system was based on the strength of the hydrogen line, which peaks in the middle here. And then the various classes were built off of that. So in the 1880s, Wilhelmina Fleming classified stars based off the strength of their hydrogen line, where the strongest lines were class A, the next class was B, and so on. And then in the 1890s, Annie Jumpkinnon realized that you could rearrange these classes to correspond to temperature. And these were O, B, A, F, G, K, and M. That is the basis of the classification we use today. So the spectral class system is O, B, A, F, G, K, M. It's based off temperature, analyzing the spectrum to figure out the temperature. So O stars are blue. They're greater than 3,000 Kelvin in temperature. They have neutral and ionized helium lines and very weak hydrogen lines. B stars are blue-white. They're from about 10,000 to 3,000 Kelvin. They have neutral helium lines and strong hydrogen lines. So some examples for low class stars, Almosarte, 10 Mosarte, sorry. B class is Rigel and Spica. A class stars are white. They're from about 7,500 to 10,000 Kelvin. They have the strongest hydrogen lines, weak ionized calcium lines, weak metal, iron, magnesium lines. These are things like Sirius and Vega. Sirius and Vega, sorry. F stars are yellow white. They're about from 6,000 to 7,500. They have strong hydrogen lines, strong ionized calcium lines, weak sodium lines, and many ionized metal lines. They're Canopus and Pyrrhicon. G-type stars are yellow, like our sun. They're from about 5,200 to 6,000. They have weaker hydrogen lines, strong ionized calcium lines, strong sodium lines, and many lines of ionized and neutral metals. These are things like the sun and Capella. K-type stars are orange, 3,700 to 5,200 Kelvin. Very weak hydrogen lines, strong ionized calcium lines, strong sodium lines, and lots of lines of neutral metals. Things like Arcturus and Aldebaran. And M-type stars are the coolest. They're red. They're from about 2,400 degrees to 3,700 degrees. Strong lines of neutral metals and molecular bands of titanium oxide dominate. Things like Betelgeuse and Antares. So this is just how we measure temperature. You might hear stars referred to by their class. Sometimes when people are looking for possible places you might find extraterrestrial life, they want to look at stars like our sun, so they talk about G-type stars. So stellar classification was one of these things where it was primarily done by women, and thus they were not credited for a very long time. These were the calculators at Harvard who were a group of women who worked at Harvard for the astronomers, the astronomy department there, and they laid the foundation of modern stellar classification. And so, yeah, the various lines you see correspond to the spectral type that reveal its temperature. The hottest is O, then B, A, F, G, K, and M, which is the coolest. Here are some example spectra for each of those stars. You can see they get simpler as you get hotter, because a lot of these lower, more complicated stuff, either, you get very complicated stuff when you have molecular spectra, those get torn apart when you get hot enough, the molecules just get ripped apart. And you get fewer lines as you get hotter because so much is ionized. So some final, some ways to remember them. Oh, be a fine girl or guy, kiss me. Only boys accepting feminism get kissed meaningfully. Those are possibilities. There's a bunch of them out there. You get a sheet of notes on tests, so you can write it down on your sheet of notes. So the 7 spectral types. This is another image showing the spectra. You can see O has strong helium lines. B has some helium and some carbon. With these are the hydrogen lines marked out. You can see they're weaker here, they get stronger. Strongest at A. You get more lines at F, G, K, and M. So as you get cooler, you get more absorption lines because less stuff is so ionized you can't make spectra anymore. So we went over these lines, but here are some other examples. No type stars, Mintaka, B type stars, Rigel. You notice that there are actually subcategories. So Mintaka is an O9, Rigel is an B8, Vega is an A0, Sirius is an A1, Canopus is an F2, the Sun is a G2, Alpha Centauri is a G2, Arcturus is a K2, Aldebaran is a K5, Betelgeuse is an M2, and Burning Star is an M5. They're just sub-classifications for further subdividing temperatures. There are also some new classes, some additional classes that have been added for funny stars that don't quite fit this. So class W are Wolf-Rayet stars. These are very hot stars, but with lots of emission lines. There's class C and S, which are carbon stars. These are red giant stars with excessive carbon in their atmosphere. So they have very strong carbon absorption lines. And then classes L, T, and Y are brown dwarf stars. These are stars so small they never quite manage full fusion. They're not actually undergoing full fusion of hydrogen into helium. But brown dwarfs are hot enough to have deuterium fusion. They can fuse deuterium into helium, but they can't form the deuterium in the first place. So they're much cooler than M-class stars. They get dust that begins to form in the atmosphere. Brown dwarfs are sort of in between gas giants and stars, that in-between state. So they're big enough that they aren't planets anymore, but they're small enough that they're not quite stars because they don't have full-fledged fusion. And they're called brown dwarfs. And we've been finding a lot more of them more recently as we've gotten more sensitive. They're hard to identify because they're small and dim. So brown dwarfs, their mass is less than 0.075 solar masses. They never become hot enough for full nuclear reactions to begin. They're failed stars. They can fuse deuterium. This is considered the distinguishing feature between, say, a brown dwarf and a gas giant like Jupiter. So the distinguishing feature between a brown dwarf and a gas giant is whether they can fuse deuterium, and that line is at about 13 Jupiter masses. So if you have a ball of gas, hydrogen and helium and stuff that's more than about 13 times the mass of Jupiter, it's a brown dwarf and will be able to fuse deuterium, but it won't be. But it needs to get above 7.5% of the sun's mass to be big enough to actually have full-fledged fusion of hydrogen into helium. So we can measure various properties of the stars. Stars come in a huge variety of sizes. So things like red dwarf stars are much smaller than the sun. And then the red giant, supergiant, and hypergiant stars are many, many, many times bigger than the sun. So here are, just for example, these are Mercury, Mars, Venus, and Earth. And then we have Earth, Neptune, Uranus, Saturn, and Jupiter. So these are planets on the top row. Then down here we have Jupiter. This is Wolf 359. You can see it's a lot smaller than the sun here. And then this is Sirius. And continuing on, Sirius here is down here, Sirius, then Pollux, Arcturus, Aldebaran. And then continuing on from there, Aldebaran, Rigel, Antares, Betelgeuse, which is really quite big, and then Betelgeuse, Mu Cephei, W Cephei, and then VY Canis Majoris is the biggest star we've ever identified. It's about 5,000 times the diameter of the sun, if I remember correctly. So stellar radii can vary greatly from something like Bernard star, which is a red dwarf, which is at 0.2 times the radius of the sun. Proxima Centauri, which is another very small star, it's actually only 0.08 times the radius of the sun. That makes it smaller than Jupiter, and that seems wrong. Up to things like Antares, which is 500 times the radius of the sun. I need to check that about Proxima Centauri. Just a second. Okay, yeah, that number is wrong for Proxima Centauri. That must be a typo. Proxima Centauri is about 0.15 times the radius of the sun. I thought that was wrong. I don't know why that typo is there. But so there's a handful of very large, very close stars that we can image directly. Most stars we just see as points. They're just too far away. But if they're very big and they're very close, so this is Betelgeuse, it's a couple AU across, we can actually image it directly. And that allowed us, actually, there was something interesting that happened with Betelgeuse recently. It dimmed. It looked like there was like a cloud in front of it. So there was a bunch of debate about what was going on with Betelgeuse. Maybe it was becoming unstable and heading towards supernova. Because Betelgeuse is, a star on its way. It's a dying star. It's a red giant. It's a supergiant, I think, actually. But it's a very large red star, but it's because it's at the end of its lifespan and has expanded. So for the majority of stars that can't be imaged directly, you need to calculate the size, knowing the luminosity and the temperature. So there's a relationship between how much light something puts out and its size and temperature. So the luminosity is proportional to the radius squared times the temperature to the fourth. There's a constant on that. So giant stars have radii between 10 and 100 times that Earth. Dwarf stars have radii equal to or less than the sun's. And supergiant stars have radii more than 100 times that of the Earth. So the sun is at the top edge of the dwarf star range. It's technically a dwarf star. And if you get 10 times the radius of the sun, you get giants. And more than 100 times the radius of the sun, you get supergiants. So the classes are Supergiants, that's luminosity class 1. Bright giants, that's luminosity class 2. Luminosity class 3 is giants. 4 is subgiants, and 5 is dwarfs. And because another thing we see is that there's differences in these spectral lines. Large stars have a much lower density. They're not much more massive. They've been expanded. There's a step in their lifespan that causes them to expand. So they have a lower, So they have a lower density. And so the spectral lines will appear more narrow in a low density environment. They don't get as blurred out. There's also differences in ionization because of the lower density in large stars. Ions are less likely to recombine with electrons. That changes their spectrum. And we can classify them into 5 categories: supergiants, bright giants, giants, subgiants, and dwarfs. Dwarfs are small and dim. Supergiants are big and bright. So the presence of absorption lines shows whether an element is present. So if you see iron lines in a star, you know there is iron in that star. Now, if you don't see iron lines in a star, you don't necessarily know there isn't iron in that star. The absence of absorption lines doesn't mean an element is not present, because you can have situations where just the conditions to generate those absorption lines don't exist. So the temperature and the pressure of a star's atmosphere determine what elements can produce lines. So you can figure out if an element is missing, but you need to know more information. You need to have some idea about the temperature and the pressure to get an idea about whether you should be seeing those lines or not. Now, pretty much all stars have the same composition. 96% of the atoms will be hydrogen and helium, and that'll be true for every star. So even if you have a star with basically no hydrogen lines visible, that means something has happened. Now, that probably just means the star is incredibly hot. Because if you get hot enough, all the hydrogen ionizes and it doesn't produce lines. But the remaining types are called metals by astronomers. So astronomers say hydrogen and helium, those are real things. Everything else is metals. Don't use this terminology with a chemist. They'll get angry at you. But while a lot of in the more general definition, if you look at what is a metal and what is not, most of the things on the periodic table are in fact metals, which is why this terminology is used. But yeah, the remaining types are called metals by astronomers. And the one thing that does vary is we get some stars will have more metals than others. These are stars that formed in later generations. They formed from dead stars, because that's how metals happen. You know, the process to generate heavier elements involves the life cycle of stars. So one of the things they're looking for right now is the very first stars in the universe, which should have basically no metals in them, and thus should have different spectra. And one of the interesting things we've seen is that we've seen very, very early stars, and they still have a bunch of metals. But you know, absence of absorption line does not mean it's not present. There are ways to figure that out, but it's more complicated. So we can that's how we can measure temperature, ionization, and what's composition of the stars. We can measure the velocity of the stars by combining 2 things. We can use the Doppler effect to figure out how fast the star is moving towards or away from us. You know, that's what the Doppler effect does. It determines radial velocity. It determines how fast something is moving towards or away from you. Because if they're moving towards you, the waves they make get squished. If they're moving away from you, they get stretched out. And then, so moving away, they get redshifted, they get shifted to longer wavelengths because the waves get stretched out. They're moving closer, they get blue shifted, the lives get shorter to shorter wavelengths. So that tells us how the star is moving towards or away from us. We can also, for side-to-side motion, we can actually see that. So if you're looking up in the sky, if something's moving towards you and it's so far away it just looks like a point, you don't observe any change. But if it's moving across your point of view, you can see it move. And that's what's called proper motion. So that's actual motion across the sky. It's very slow, but it is noticeable over long time periods. So the star with the largest proper motion is Bernard's star. To see a nice clear motion, you have to wait like years. I think the example I showed had two pictures 22 years apart. So there's motion across the sky, but it's very slow. And we can combine these two to find the actual velocity of the star. So you can combine the radial velocity, the proper motion, and the distance. So with the proper motion, it's movement across the sky, and knowing how far away it is, you can get its side-to-side velocity. You can combine that with its radial velocity from the Doppler effect to get its actual space velocity. And this is the true motion of the star through space. So proper motion is what changes the constellations over time. So 50,000 years ago, the Big Dipper looked like this. This is it today. If you look at the proper motion, these stars are all moving up and to the left. These two are moving down and to the right. So in 50,000 years, it'll look more like this. So the constellations are very slowly changing. But proper motion gets smaller the further away you are. So it's just not very big. Additionally, it turns out you can use the Doppler effect to figure out how stars are rotating. Because when you have a ball that's rotating, one side is moving towards you and one side is moving away from you. And so the side that's moving towards you gets slightly blue shifted. The side that's moving away from you gets slightly red shifted. And what this does is it causes spectral lines to go from being nice and sharp to being wider and broader. And using this, we can figure out the rotation rate of stars from how they brought it. And you do the same for things like galaxies and other stuff. It's a very useful tool for figuring out how things are rotating. So stars are classified based on their temperatures, O, B, A, F, G, K, and M. New classes have been added for unusual stars and brown dwarf stars, and the spectrum of a star tells us about its size, velocity, composition, and rotation. We can get a lot of information from the spectrum of a star, which is why every telescope with the actual research telescope has a spectrometer attached, and usually multiple spectrometers. So here's a short video about some of the patterns we see among the stars.
One of the best ways to visualize the patterns among stars is with what we call a Hertzsprung-Russell, or HR diagram. At its most basic, an HR diagram is simply a graph with surface temperature, or spectral type, along the horizontal axis and luminosity along the vertical axis. Notice that, for historical reasons, surface temperature declines from left to right. Most stars have properties that put them along a rather narrow ribbon called the main sequence that runs from the upper left to the lower right of the HR diagram. Main sequence stars, which include our Sun, generate energy by fusing hydrogen into helium in their cores. When we measure the masses of stars along the main sequence, we find that the least massive are the cool red stars at the lower right, and mass increases as we go upward. Lifetimes increase in the opposite direction because massive stars are so much more luminous than less massive ones. As a result, they use their hydrogen fuel at a prodigious rate, leading to the general rule that more massive stars have shorter lifetimes. Besides the main sequence, we find stars in a few other regions of the HR diagram. To the upper right are giant and supergiant stars, which get their names because of their large radii and luminosities. As we'll discuss in later chapters, these stars are nearing the ends of their lives. To the lower left are white dwarfs, which have hot surfaces but low luminosities because they are very small in size compared to main sequence stars. These stars are essentially dead because they are no longer able to generate energy through nuclear fusion. Overall, the HR diagram is one of the most important tools in astronomy, so we'll discuss it in more detail in the separate narrated figure titled the HR diagram.
So, in the early 1900s, two astronomers, Henry Norris Russell and Einar Hertzsprung, created a graph of stellar properties. They graphed luminosity against spectral class, though originally the very first one was graphing luminosity against, I think, the strength of one of the lines or some other property that increased as temperature decreased, which is why high temperature is at the left and low temperature is at the right. Because the very first version of this graph wasn't graphing against temperature. It was graphing against another property that was inversely correlated to temperature. And they found a relationship between the temperature and the luminosity for most stars. So they found that for 90% of stars, there's a relationship where the higher the temperature, the higher the luminosity, the lower the temperature, the lower the luminosity. They follow this sort of path down the center, which is known as the main sequence, because 90% of stars sit on it. And these are bigger and shorter lived, and these are smaller and longer lived. So the HR diagram plots stellar luminosity against surface temperature. This is an HR diagram of a few prominent stars. It turns out because of what makes a star prominent, it's a very random distribution of points. But if we add more stars, we get to start to see some actual patterns. So these are the 80 closest stars to us. Note that the dashed lines are constant radius. The darkened curve here is called the main sequence. And this is where most stars are. And it's also indicated is the white dwarf region down here, where these stars are very hot but not very luminous, as they are tiny. White dwarf stars are on the same scale as Earth for size. They're very small. But yeah, so we see things like Proxima Centauri, Red Star, down here. And an HR diagram of the 100 brightest stars look quite different. We see a whole bunch of stars out up here in what's known as the red giants region. And we see sort of the top half of this main sequence. These stars are all more luminous than the sun. We get the red giants and the blue giants. And the brightest stars in the sky appear brightest because of their enormous luminosity and not their proximity. So here's an HR diagram for something like 20,000 stars. We can see the main sequence has lots of stars on it. 90% of the main stars lie in the main sequence. And then the other 10% is sort of split between red giants and white dwarfs. You see different distributions for that, mainly because it's varies how easy it is to detect white dwarfs. As you can see here, main sequence stars make up about 90% of the stars, and then white dwarfs, giants, and supergiants make up the remaining 10%. And if you plot an HR sequence, you have an x-axis, you have a y-axis, The x-axis is temperature, starting from high temperature going to low temperature. The y-axis is luminosity, starting from low luminosity going to high luminosity. And if we wanted to locate various things, this line here is the main sequence with the sun in the middle-ish. Up here are the giants, up here are the supergiants, down here are the white dwarfs. And the largest stars are up in the corner. Because radius goes up as you go from the lower quarter up to the higher. So the largest stars are up here, supergiants, giants. This is the main sequence with the sun. These are white dwarfs. So the second drawing was done by the person, the source of the slides. The first drawing was done by me. You can see the difference there. So we find that larger and more massive stars are on the upper left. The biggest stars are up here. Along the main sequence, the larger and more massive stars are on the upper left. The smaller and less massive stars are down here. So this is along the main sequence. And the thing that determines where you land on this main sequence is your mass, it turns out. The primary thing that determines your life cycle as a star is your mass. So these are small light stars. These are big heavy stars. And this has been confirmed with star formation models. Stars will change their temperatures and luminosities over their lives. Thus, their position on the HR diagram will change, though they will spend most of their lives sitting on the main sequence, not moving much. So while a star is in a nice stable equilibrium like our sun is, it sits on the main sequence, doesn't do much. And it turns out the reason 90% of stars are along the main sequence is because stars spend about 90% of their life on the main sequence. And then the other states are other portions of their lifespan. So what is the significance of the main sequence? Well, we see some things as we get much smaller. We have small stars down here, big stars up here. And the lifetimes get shorter as we go here. So the sun has a lifetime of about 10 to the 10 years or 10 billion years. As you head down, the lifespans get longer, 10 to the 11th. This is 100 billion. You can get up something like 1 trillion years. And then as you go up, the lifetimes get shorter. So stars up here that are, maybe 10 to 30 times the mass of the sun have lifespans in the tens of millions of years instead of tens of billions. And they can even be shorter than that as they get bigger. The maximum size for a star is about 100 times the mass of the sun. Above that, stars just aren't stable. So main sequence stars are fusing hydrogen into helium in their cores like the sun. Luminous main sequence stars are hot, blue. Less luminous ones are cooler, yellow or red. So these are both bigger and more massive and hot. These are smaller, less massive, and cooler. So these end up significantly dimmer than these. And if we look at mass measurements, we see the hot blue stars are much more massive than the cool red ones. And the hot blue stars are also bigger than the cool red ones. And the mass of a normal hydrogen fusing star will determine its luminosity and its spectral type. So the thing that determines where you end up on this main sequence is your mass. And the core temperature of a higher mass star needs to be higher in order to balance gravity. And a higher core temperature boosts the fusion rate, leading to more luminosity, but also a shorter lifespan. Wow. It's because they consume fuel at a faster rate, and the rate of fuel consumption increases faster than the amount of fuel does. So let's talk about some extremes of stars. The smallest stars are in the lower left in the HR diagram. These are white dwarfs. They're very hot, but very dim. And since the amount of light you put out is proportional to your temperature to the fourth power, that means they have to be times the radius squared. Well, if they're very hot but dim, they have to be tiny. And these are white dwarfs. These can be as small as the Earth. But they're incredibly hot. Hundreds of thousands of degrees Kelvin on the surface. And then we have the biggest stars are up here. These are the largest stars. They're very cool, but they're bright. So they're huge red stars. Along the main sequence, the most massive stars are in the upper left. The least massive stars are in the lower right. But that's only along the main sequence. Things get more complicated over here about mass. And the densities of stars, the least dense stars are up here in the upper right, and the most dense stars are down here in the lower left. White dwarfs are incredibly dense. A teaspoon of the matter in white dwarfs would weigh 50 tons. And they aren't the densest objects out there in the universe. We'll get to those, but white dwarfs are incredibly dense. So let's look at some properties. The luminosities vary from a 10,000th of the luminosity of the sun to 1,000,000 times the luminosity of the sun. Temperature varies from around 3,000 Kelvin for red dwarf stars, small, cool red stars, up to 50,000 Kelvin for hot white stars. And the mass from the period and average separation of binary stars in orbit, we see the mass of stars varies from around 0.08 times the mass of the sun, or 8% of the mass of the sun, to about 100 times the mass of the sun. If it's less than 0.08 times the mass of the sun, it's a brown dwarf. It doesn't qualify as a star. And if it's more than about 100 times the mass of the sun, it will turn out to be unstable. The luminosity, there's enough energy produced to basically blow off the outer layers of the star. So it won't stay 100 times the mass of the sun. The dimmest stars are the smallest stars at 0.08 times the solar mass. The brightest stars are the largest stars at 100 times the solar mass. The coolest stars are the smaller stars. The hottest stars are the biggest stars. We can also look at how mass is related to lifetime. A star's life expectancy, the sun's life expectancy is about 10 billion years. We're about halfway through the lifespan of the sun. This is until the core hydrogen, which is about 10% of the total hydrogen in the sun, gets used up. When that happens, the core will collapse and the sun will become a red giant, and the Earth will be screwed. Well, actually, the Earth is probably screwed well before then, but the life expectancy of a 10 solar mass star, it has 10 times as much fuel because it's 10 times as massive, but it uses it 10,000 times as fast. And so it's only about 10 million years. And that should be an equal sign. or an approximate sign. I think something got messed up in the formatting. I can. Sorry about that, but 10 million years is 10 billion years times 10 divided by 10 to the 4th. 10 times as much fuel, but we consume it 10,000 times as fast. So we only have a lifespan that is something like 1,000th as long. So 10 million years. So 10 million years is about 10 billion years times 10 divided by 10 to the 4th. Now, if we look at a 0.1 solar mass star, it only has 1/10 as much fuel, but it uses it 100th of the speed. So that ends up having a lifespan of about 100 billion years. Because while it only has 1/10 of the fuel, it uses it 100th of the speed, so it lasts 10 times as long. So if you have something that's 1/10 the mass of the sun, it has a lifespan of about 100 billion years. And that's getting down towards the smallest stars you can talk. So high mass stars have high luminosity, they're short-lived, they have a large radius, they're blue, they die violently and spread their remains about the universe. Low mass stars have low luminosity, they're very long-lived, they have small radius, and they're red. Brown dwarf stars have a mass of less than 0.075 solar masses, or about less than 79 times the mass of Jupiter, and they never become hot enough for true nuclear reactions to begin. They're failed stars. They can fuse deuterium, which is considered to be the distinguishing feature between a brown dwarf and a planet. If they're less than 0.012 solar masses, or about 13 Jupiter masses, deuterium fusion is no longer possible. They then get classified as a planet. We needed a line, so we defined it based on deuterium fusion. So let's talk about what these non-main sequence stars are: giants, supergiants, and white dwarfs. So stellar properties depend on both mass and age. Those that have finished fusing hydrogen to helium in their cores stop being on the main sequence. So when you're on the main sequence, you're doing regular old star stuff. You're fusing hydrogen into helium, making energy, and just sort of sitting there. After you run out of hydrogen, all stars will become larger and redder. What happens is the core of the star collapses, gets hotter, heats up the layers above it, and causes the rest of the star to expand. And this leads to giants and supergiants. Smaller stars become giants, larger stars become supergiants. They're qualitatively different because larger stars that become supergiants are big enough to have more stages of fusion going on. And then most stars, after fusion has truly ceased, they blow off their outer layers, just the dead core of the star remains, and that is a white dwarf. So the white dwarf is basically the corpse of a moderately sized star. So the sun will eventually become a white dwarf. Stars up to, think about 8 to 10-ish times the mass of the sun become white dwarfs. There's a limit. If the core is big enough, something else will happen. Bigger stars do something different. But most stars end up small and white after fusion has ceased, leaving behind white dwarfs. So here are some examples. Betelgeuse is a supergiant star. It's 900 solar radii across. It's 120,000 times the luminosity of the sun. Aldebaran is a giant star. It's 44 solar radii across. The sun here is a main sequence star. And Peroxon B is a white dwarf. And it is similar in size to Earth. It's about 0.1 solar radius. And you can see Earth is similar in size. So giants are supergiants are, more than 100 times the size of the sun. Giants are more than 10. So giants are far larger than main sequence stars and white dwarfs. Giants, supergiants. And then white dwarfs are tiny. Again, white dwarfs are similar in size to the Earth. They're similar in mass to the sun. So big difference there. So they're super dense. But they're similar in size to the Earth. So if we plot luminosity versus temperature, we can see patterns in the types of stars. The HR diagram shows how these quantities are related. And by studying how stars move on the HR diagram, we can get an idea of their life cycles. Stars spend the majority of their lives in the main sequence, but will change positions as they age and their temperatures and luminosities change. And so when we talk about how stars evolve and we go through their lifespans, we'll talk about how they move on the main sequence. And we can make a census of the stars. We can look at what types of stars are typical. Interestingly enough, these are not the stars we see in the night sky. The stars we see in the night sky are primarily large, bright stars that can be seen over tremendous distances. Basically, if we look at stars within 21 light years of the sun, there are only a couple of spectral type A. There are no B or O. There's one spectral type F. There's about 7 similar G-type stars like the sun. There's 17 K stars. There's 94 M stars. There's 8 white dwarfs. And there are at least 33 brown dwarfs. That number is probably underreported because brown dwarfs are really hard to detect because they're small and dim. So the average star is much smaller and cooler than the sun. How common are brown dwarfs? They're probably a lot more common than this table shows because they're very faint and we're constantly detecting more of them as we get better at detecting them. They don't put out a lot of light because they're not fusing. So they're not very hot. So we have a few other ways to detect them, but they're hard to see because they're small and dim. And so this is one of these issues that you have often when you're doing observational stuff or there's various studies, something known as a selection effect. There's a similar thing going on with our, if you look at exoplanets that have been found, they have certain trends, but that is again a selection effect. So selection effects are effects that are caused by the method you're using to observe things. The fact that the stars we see at night are not typical of the stars in general is an example of a selection effect. Because the stars we see at night are all stars that have an apparent magnitude above a certain value, below a certain value. Basically, bright stars are easy to see. You can see them for hundreds and thousands of light years. While faint stars are hard to see even if they're close by. Which means if you look out into the night sky, you're going to see the bright stars, the really big bright stars, and you're hardly going to see any of even the nearby faint stars. So because of this selection effect, we're seeing an unusual distribution of stars. We're seeing the more unusual stars. We see O and B stars, we see red giants, supergiants. But just to be clear, the nearest red giant is nearly 100 light years away. There aren't any close by. And the nearest O-type star is nearly 500 light years away. Those are a long way away. And there are other selection effects that happen. So up until very recently, almost all the planets we found around other stars were both very big and very close to their star. And this is, well, this is not really an effect of very big, very close to their star planets are common. It's that the bigger a planet is and the closer it is to the star, the easier it is to detect. Our methods for detecting planets work better the bigger and closer the planet is to its star. Now, we have found there are ways you can correct for selection effects. So you can go, okay, let's look at all the stuff we found in a certain area or something like that. Let's look at like the density of these. So like that table where it was, let's look at all the stars within a certain distance of the sun. That helps correct for the selection effect that it's easier to see bright, far stars. There are ways to correct for that. If we do correct for that, we do see a lot more giant planets close to their stars than we expected. Because there are ways to correct for this, especially now that we've seen a lot more planets that are smaller. And it's just like part of it, we're confused about this because we don't have a good explanation for how this can happen. Our understanding from our solar system is that big planets should be further away from their sun, not with orbits, smaller than Mercury's, and masses bigger than Jupiter's. That's not uncommon. But we'll get to that when we talk about exoplanets. Yeah, we've seen a lot of exoplanets, but they have an interesting distribution. So lots of stars are in. So how do we figure out other information about stars? Well, one of the things we've seen is important is the mass of stars. How do we figure that out? Well, turns out lots of stars are in binary pairs. In fact, most stars are in binary or are in groups of 2 or more. Solitary stars like our sun are not the most common situation. And this is great because if 2 stars are orbiting each other, we can use Newton's modified version of Kepler's third law to figure out their masses. Measurement of their orbital motion allows us to determine the masses of the stars. If you can see both stars, that's a visual binary. Then you can observe their masses directly. But that's not always the case. Sometimes the star is so far away and the stars are so close together, or both, they just appear as a single star. But you'll see you could have spectroscopic binaries where basically you have double spectra. You'll have 2 spectra. You'll have varying spectra as it orbits. They allow the measurement of motion and the period, and you also have eclipsing binaries, where once one star passes in front of the other, the total dims. So you get a pattern like this. So when the smaller star passes in front of the bigger star, you get this dip. When the smaller star passes behind the bigger star, you get this dip. And for eclipsing binaries, you can measure their orbits with intensity variations. So here we see light from both A and B. Here we see light from all of B and some of A. Here we see A and B. Here we see light only from A. And that's an eclipsing binary. And that cycling allows us to identify the various masses of stars. So if we're going to figure out the mass, we need something orbiting a star to figure out its mass. Luckily, binary stars are common. We can determine their mass from the orbit. The three types of binaries are visual binaries, where you can see both stars like this. That's the easiest way to measure the orbit. You just track the two stars orbiting each other. Spectroscopic binaries, we can only separate the two stars spectroscopically, but not visually. And eclipsing binaries, where the star will dim when an unseen companion passes in front of it. And the orbit of a binary star system depends on the strength of the gravity between the stars. So the visual binary, eclipsing binary, and spectroscopic binary, about half of stars are in binary systems. For a visual binary, well, you just take pictures over time, the stars orbit each other, you could determine the orbits and figure out the masses of the stars. In a spectroscopic binary, we can separate the two stars spectroscopically, but not visually. You'll basically get a double spectrum. You get the spectrum from each star, because one star will be blue shifted and the other will be red shifted. And so their spectra will be separated. And you can measure the speed of each of these and the period, and that gives you enough information to work out their orbits, and from there, their masses. Because you can get information about each star individually. One side of the orbit, RB, is approaching us, so its spectrum is blue shifted, while on the other side of the orbit, it's receding of it, so its spectrum is red shifted. And there's going to be a similar effect on star A, but opposite to B. So you can determine the orbit by measuring Doppler shifts. And then you can measure the masses of stars in an eclipsing binary. The star will dim when an unseen companion passes in front of it. This is also one of the main ways we've been detecting exoplanets, because stars dim when the planet passes in front of them. So there's a big sky survey. There's a satellite that's just taking pictures of lots and lots of stars over and over again and seeing how they dim over time. There's a few of these surveys out there. So you could measure periodic eclipses. And how do we figure out the mass of a star? Well, we use Kepler's third law. In the solar system, the semi-major axis cubed is equal to the period of revolution. And it turns out if you do a little math with Newton's law of gravitation, you can get a version of this where this was modified by Newton to give the semi-major axis cubed, the distance of the star cubed, equals mass 1 plus mass 2 times the period squared. So if we can determine the semi-major axis and the period of the orbit, we can figure out the mass of the system. If we measure distance in astronomical units and p in years, the mass will be in solar masses. Otherwise, there's just a constant here, which you can work out from Newton's equations. It's just what 4 pi over big G or something. It's just a standard constant. So yeah, here, period squared is 4 pi squared over big G, mass 1 times mass 2 times average separation. So there's just a constant in there. The direct mass measurements are only possible for stars in binary systems. And we can measure the orbital period, the orbital separation, or the orbital. If you have 2 of these 3, you can get all the information to find the masses of the stars. So the period, the time it takes to make an orbit, the separation, the radius, or the velocity. Usually you can get the period and then one of the other 2. And the most massive stars are 100 times the mass of the sun, and the least massive stars are 8% of the mass of the sun. The largest stars seem to be limited to about 120 solar masses because radiation pressure above 120 solar masses, basically the stars become so bright, they push off anything more that would be added to the star. The radiation pressure could exceed the gravitational force. They get so bright that they actually will push away the outer layers of the star with the light alone. The theoretical upper limit is around 300 solar masses. But this is for a star that contains only hydrogen and helium. So no modern stars contain only hydrogen and helium. Because basically this process gets interfered with if you add some heavy elements that help push harder. And the lowest mass stars are about a 1/12 of a solar mass, because below this it never gets hot enough to fuse hydrogen into helium and you get a bright. And I think I will stop around there. I will resume with stellar masses on Thursday. Remember, by Friday or Saturday, you need to get at least half of the assignments submitted. And make sure you either have all your tests done or you have a plan to make up any tests you've missed. Okay.